thanks to Carlos for inviting me, and congratulations to the Gravity group of Aveiro. I just joined very recently, so I'm actually maybe in the wrong, not quite in the right session, but I couldn't make it this morning in person, which I regret, but I guess this is the best I can do to tell you a bit about what I'm doing and who I am. I'm from the University of the Algarve. I joined in the beginning of this year together with my colleague Pablo Sa, who is there, who you maybe met, and also Nenad Manojdovic. And as I just recently joined, I decided simply to give a quick, to let you know a little bit about what I've been working on recently, and hope then that this maybe I can develop this further, maybe get collaborations going, or more collaborations going, because I had one collaboration already with someone from the group. So just let me start a quick introduction. So I come from particle physics, and I've also been interested in gravity, of course. As you probably are all aware, the standard model and general relativity explain very well nature, but I just not quite complete. There are some mysteries left here. I've listed a few of the issues that are remaining here. Neutrinos are not massless as the standard model thought they were. So we may need to add something there, right-handed neutrinos. And then on the more cosmology gravity side, we don't know about dark matter exactly. The standard model does not necessarily provide a suitable dark matter particle. So maybe we need to add some strange matter. Maybe we need even to change gravity, get something Mond-like, who knows. Standard model cannot, and the current theories don't really have a good explanation for accelerated expansion of the universe. We have here the CP violation of the standard model does not explain the matter-antimatter asymmetry. Hubble tension is a mystery. We have a discrepancy between the local and the CMB Planck measurements. Maybe here something needs to be changed. We need to understand this. Okay, so there are some mysteries there, and maybe this mystery has to do with our incomplete understanding of the link between quantum field theory and gravitation. So maybe it's hidden in quantum gravity. We don't know. So how could we learn more about this? Something I've been working on in the past few years, in fact, already in the past 2 decades, is the possibility of space-time symmetry breaking. So the idea is that there may be Planck scale physics that we would like to know about, but we cannot directly measure. So we look for indirect methods. And a promising approach, maybe a promising approach, is to look at principles of the standard model and general relativity that may be modified or have to be broken in a unified underlying theory of quantum gravity. And so the idea is to look for the space-time symmetry of local Lorentz invariance that may be broken in an underlying theory, and that there are some tiny effects, but nevertheless measurable effects. Some models of quantum gravity and other fundamental models, in fact, have already given such a breaking. I've listed here a few models. Strength field theory, non-commutative space-time, for instance, gives you directly Lorentz invariance breaking. Massive gravity gives this. Horava gravity breaks directly Lorentz invariance. Okay, so if any of these theories are realized in nature, that may be a consequence. Other space-time symmetries, by the way, may also be broken as a consequence of this local Lorentz invariance breaking, such as CPT and diffeomorphism invariance. Okay, so how do you go around describing such fundamental symmetry breaking in a consistent way. So there are two ways to go. The first one is to look for an effective field theory description. So what you do is you say, well, there is a broken space-time symmetry, so you assume the existence of a background tensor field or more tensor fields that as a relic of the underlying theory get a non-zero vacuum expectation value, breaking Lorentz invariance. And then these fields can couple to standard model fields. So these are not standard model fields, or presumably not, and to the metric. And so you get extra terms that are not in the standard model Lagrangian, namely that coupled to those background fields. And that gives you additional terms that are Lorentz scalars, but are then standard model fields coupled to these tensor fields. So they are scalars, but with these vacuum expectation values included. The terms that you include, they could be of any mass dimension. So you can get an expansion in terms of arbitrary increasing mass dimension and get so an effective field theory description. Okay, so then you add that to the standard model Lagrangian you have and have of general relativity, and then the total sum, who knows, might converge theoretically to your fundamental theory, which you're not going to find, but that's the idea. Okay, so the effects of then these coefficients, of these extra terms, you measure as a detection of a Lorentz violating effect. So the values of the coefficients of the vacuum expectation value times the coupling constant then gives you Lorentz violating effect, presumably very small. Okay, so you can then try to measure them, or you find bounds, and lots of bounds have already been found, either experimentally or by astrophysical observations. I'll give an example in a bit. Maybe it's useful to note that the standard model extension, which is this effective field theory is called, is not a fundamental theory. It's not even a predictive model, but it's a test framework, something like the parameterized post-Newtonian network for gravity. Okay. One example that is nice to consider to get the idea, that is the photon sector, the pure photon sector. So you have Maxwell theory, and then you add the other possible terms here that you can actually add, that are taken to be to conserve gauge invariance. So they're built of the F mu nu, of the field strength. Here you see an explicit vector field. So actually, is like the Lagrangian density is actually not gauge invariant, but nevertheless the action is. Okay, so if you integrate, the variation of this is zero in the action. The action is gauge invariant. There are here some heads. These are coefficients with 4, and here with 1 Lorentz index. There are heads sitting there. That means that they are actually operators with derivatives, the space-time derivatives that are not explicitly written here. So they are power series expansion of coefficients with derivatives of arbitrary order. So in fact, it's a whole bunch of terms here sitting in a short formula. Okay, there is the second term is maintains CPT invariance. This one breaks CPT invariance. They both break Lorentz invariance, and they yield modified Maxwell equations, including frequency-dependent speed of light, vacuum and anisotropy, birefringence, not for all terms, but so there's all kinds of effects here you can have. So there are boundless, countless bounds, either laboratory bounds or astrophysical bounds. For instance, a very recent paper we published last month in PRD together with Merce Guerrero, who was a postdoc of the Aveiro group until last month. I think she has moved to another job this month. Okay, so that where we given a general method to give bounds on these coefficients based on data that are already published, coming from gamma ray burst data. That give very precise bounds, or very tight bounds on the speed of light, and therefore on these coefficients. Another example is a few terms from the pure gravity sector. So you have the Einstein-Hilbert action, and then here I list two terms here in that violate Lorentz invariance. The couplings of the background tensor to the Ritchie tensor and to the Wild tensor. Okay, so they give all kinds of effects also. For instance, they affect gravitational wave propagation. And you can use them if you have data from gravitational wave propagation to extract bounds as well. Here's a paper that is very recent. Oops. Another way to do it, so this was effective field theory. You can also use models of Lorentz violation that I had already mentioned earlier. So they are either models, let's say point models, or approximate models, or really supposedly fundamental models. And in that case, it's actually very useful to match the parameters. They're going to give you prediction for Lorentz violation in terms of the parameters of those models. And it's very useful to actually match the parameters of these models to the corresponding parameters of the standard model extension, so that you can check the experimental signals and even see if there are already existing bounds, because there are many bounds already measured, as I mentioned. Okay, so here are a few of these models: bumblebee models, Einstein ether models that have been very popular and actually continue to be so. Massive gravity, Horava-Litchfield gravity, already mentioned this. Okay, so all of these would fall into this in this section. I just flash you the bumblebee model that really has hundreds of papers written on it at this moment. So you have here Einstein-Hilbert action, cosmological constant, and then here the rest of the terms come with the bumblebee. So the bumblebee, it uses a vector called B that you couple in any possible way to the curvature, or to the Ritchie tensor, to the Ritchie scalar, and you can do it with various different possible. I have here the kinetic terms that are quadratic in B, and then most importantly, a potential that you assume to be a function of the square of the length of the B field. Okay, so then that potential can be either smooth. I'll give you an example. Now, what is important is that it forces the expectation value of B to be non-zero. So, for instance, you see here this quadratic potential, quadratic in B mu, would do that. Or what has been used also is a Lagrange multiplier potential, where you force actually the expectation value of B mu to be an exact value. Here it's equal to an either a positive or a negative value, depending if you want time-like or space-like value. The Einstein ether model, for instance, does that. For time-like, it always uses time-like B mu, which you can also do space-like actually. Here, this model breaks gauge invariance, so you have 3 local degrees of freedom rather than 2 for the vector field. It's not a gauge field. And you can get all kinds of solutions that are typically deviations from general relativity, like Schwarzschild-like things, Kerr-like solutions, cosmological solutions, brainward solutions. So there are like dozens or even hundreds of papers on this. Okay, so I'll leave it at that. So I leave the conclusions here. So current description incomplete, and so this is just one method to try to to know more about the fundamental theory of quantum gravity or fundamental theory of nature underlying standard model and general relativity. Look for breaking of local Lorentz range as a relic effect, and use this effective field theory description of the standard model extension to try to isolate the experimental signals and then maybe match them with models. So I would be very happy if in the future I can continue to maybe work with the members of the other members of the group and get ideas of maybe how to incorporate this in strong gravity, which I haven't done much. Okay. Thank you.
Thank you very much. Thank you. So thank you, Rob, for yet another perspective of the research that's being done in the group. Just for the sake of clarifying to the audience, so Rob is a member of the group, and actually because of the agenda, he couldn't be put in the first session, the last one of the morning, so he was moved to this one. Rob, so we have some new group t-shirts, so we'll save one for you. I'll send one to you via Paulo, if Paulo
okay,
is
great.
okay, and also one to Nena. So thank you very much, and see you soon, hopefully.
Thank you. Yeah, sure.
Okay, and let's move on to